Welcome to Shapers Learning Academy and as well as the Deep Learning course module number 7. In the previous module number 6, we had a soft introduction about the convolutional neural networks, and this module is dedicated to CNN alone. So what is CNN? Convolutional neural network. A convolutional neural network is a type of artificial neural network used in image recognition. Image recognition has opened up a great network and a great market for artificial intelligence products, and hence the CNN is a backbone behind image recognition. So a convolutional neural network is a type of artificial neural network used in image recognition and processing that's specifically designed to process pixel data. So any picture that we have is actually a collection of pixels, right? So any data that has spatial relationships is ripe for applying CNN. When we speak about spatial relationships, it's nothing but the relationship between the pixel images, the relationship between the colors of the pixel. So any data that has spatial relationships is ripe for applying for CNN. CNNs are powerful image processing and artificial intelligence that uses deep learning to perform both generative and descriptive tasks, often used for machine learning vision that includes image and video recognition along with NLP. What is convolution basically? So convolution is a mathematical operations of two functions f and g that produces a third function. So convolution is a mathematical operation on two functions that produces a third function that expresses how the shape of one is modified by the other. So the term convolution refers to the result function and to the process of computing it. Now let's try to understand as how an image is being processed by a CNN. So the obvious part. So when you see an image something like this, how do you process? The first step is to identify the edges, the horizontal as well as the vertical edges, right? So that's a basic step. Either be a computer or our vision first tries to understand where the edges of the image lies. So that's what we are going to understand in the subsequent slides. So here, this is how it processes and gets the vertical images. This is the first step of convolution, and this is the second, where we try to identify the horizontal edges. Now let's understand the mathematics of convolution. As you know, the image that we were discussing in the previous slide will have some pixel values, right? So this image is actually a collection of pixels, and the intensity of pixels brings out the colors. So each and every unit is a pixel and it has its own respective value. So just imagine this is the matrix of your image, the pixel matrix of the image, which is of the dimension 6 cross 6. So how do you convolve? You're supposed to use a filter. So as we know, our objective is to detect these edges first. So how do we detect the edges? We detect by convolving the image. And here, when you are convolving the image, you are supposed to use a filter, something called as a kernel filter, and this kernel filter will help us in convolving. The convolution takes place in the way something like this. So here our filter gets superimposed on the first section of 3 cross 3 out of the 6 cross 6 matrix. So picturize placing this 3 cross 3 matrix over here. Once after placing, you get the value something like this. So you are supposed to multiply and as well as add the values. Coming again, we have a matrix 6 cross 6, which is nothing but our input raw image. We have a filter, kernel filter 3 cross 3, of values as such. There are multiple filters, and this filter has these values. So superimposing of this filter on this primary image and multiplying the respective values with the pixels, something like this: 3 into 1, 3 cross 1, plus 0 cross 0, plus 1 cross minus 1, plus 1 cross 1, and so on until the 3 cross 3 is being superimposed completely. We get stride number 1. Similar way, this 3 cross 3 filter will pass on the stride, the entire picture in strides. So when the 3 cross 3 matrix or the filter is placed here, we call it as stride number 1. When it passes one step ahead, we call it as stride number 2. When crosses one step ahead, we cross stride number 3. Similar way, this filter parses this entire matrix and gives us a convolutional value of a matrix 4 cross 4. So a 6 cross 6 image, when parsed or strided by a filter of 3 cross 3, we get a convolutional value of 4 cross 4. Here's where you get another example where you have an image of 6 cross 6 and you have a kernel filter which strides step by step and passes this entire data set, and we get a 4 cross 4 matrix. So this is a very common technique to identify the edges or detect the edges. So the higher pixel values represent the lighter portions of the image, whereas the lower pixel values represent the darker portion of the image. So when convolve results in a 4 cross 4 matrix where you be able to detect the edges, the vertical edges in this case. The same concept for an horizontal edge where the filter changes. Now let's understand certain tools which helps in the convolution faster. Here we have a concept called as spoolig layers. Spoolig layers are generally used to reduce the size of the inputs and hence speed up the computation. For every consecutive 2 cross 2 block, a pooling layer concept takes up the maximum number. Hence we have applied a filter of size 2 and a stride of 2. Apart from max pooling, we can also apply average pooling, where instead of taking the max numbers, we take the average numbers. So there are two types of pooling layer concepts, where one is to stride a 2 cross 2 matrix and take up the topmost value. So it is, if it is stride number 1, it is 9, and where stride number 2, we take number 2, stride number 3, we take the maximum value 6, the stride number 4, we take the maximum value 3. So this one concept, whereas we have another concept where we stride and take the average of the 4 values. So 9 plus 3 plus 1 plus 2 divided by 4. So that comes the value here. That's in the average pooling. That's called as average pooling. Here, let me explain you one problem statement that we face with convolutional neural networks and a resolution for the same. See here, as you see, here there's an input picture 6 cross 6 matrix which is being convolved with the filter 3 cross 3, and the output is 4 cross 4. Or 6 cross 3 matrix convolved with 3 cross 3 filter gives a output of 4 cross 4. So what is one main disadvantage which is actually visible is actually the removal of the edges. We lose the edges. Alright? So this one problem statement. Let's come to the theory now. So we have seen that convolving an input 6 cross 3 dimension with a 3 cross 3 filter results in a 4 cross 4 output. We can generalize it and say that if the input is n cross n, 6 cross 6 or n cross n, and the filter size is f cross f, then the output will be n minus f plus 1 into n minus f plus 1. We are right? So 6 minus 3 is 3 plus 1 is 4. So if the input is n cross n, filter size is f cross f, the output is n minus f plus 1 into n minus f plus 1. So the explained disadvantages: every time we apply a convolutional operation, the size of the image shrinks. Yes, a 6 cross 6 becomes 4 cross 4. Pixels present in the corner of the images are used only a few number of times during convolution as compared to the central pixels. Yes, hence we do not focus too much on the corners since they can lead to informational loss. So any layer that is lost leads to an informational loss. So to overcome these issues, we can pad the images with an additional border. So instead of a 6 cross 6, you can have an additional padding, something like this. I'll make the matrix 8 cross 8. So applying the convolution of 3 cross 3 on it will result in the 6 cross 6 matrix, which is the original shape of the image. This way the padding comes to the fore. So input is n cross n, padding is p, filter size f cross f. So the output is n plus 2p, because you have added 2 padding layers, n plus 2p minus f plus 1 into n plus 2p minus f plus 1. So here the loss is actually not there. You don't lose any layers of the image. So there are 2 common choices of padding. One is called as a valid padding. It means that there is no padding. If you are using valid padding, the output will be n minus f plus 1. This is the normal state, expected state. Whereas here you apply padding, you get this formula, n minus 2p minus f plus 1, which is equals to n. The final connect. So what are fully connected layers? Fully connected layers are an essential component of convolutional neural networks, which has been proven very successful in recognizing and classifying images for computer vision. The CNN process begins with convolution, as we saw in the previous pictures, where actually it identifies the edges and it convolves with the help of kernel filter. So the CNN process begins with convolution, pooling, breaking down the image into features and analyzing them independently. The result of the process feeds into a fully connected neural network structure that drives a finite classification decision. So thanks for your time, thanks for your patience, and thanks for your learning.